Hello. All right, guys. Thank you for showing up. I really appreciate it. Show of hands, how many of you enjoy recreational math? Okay, applaud everybody else, because we're going to do some of that today. This is scientific calculations on EVM, or Huffing gas, for 38 decimals of precision. I made some nice animations, and you will not see them today, because my computer's not working right. The main point today is how to perform calculations without leaving the blockchain and without being satisfied with 18 decimals of precision, which is normal. Everybody know what WAD math is? No? You do? Yeah, okay, good. So we'll talk a little bit about that. Let's just get right into it. What are scientific calculations? What I mean by this is generally transcendental functions, like the exp, that's my favorite, natural log, square root of x, and then, of course, powers. And this last one, anybody know what this is? Lambert W. It's a special one that cannot be represented with primitive functions. So yeah, for scientific calculations, we also need them decimal and signed. So your regular uint 128 is not really good enough for these curves, and they must be thoroughly tested with consistent precision so that there's no spaces in the domain where numbers come out all wrong. Why do we need high precision? Yeah, we can't leave dust in a contract because it won't close. And if the rounding isn't right in the other direction, the call will revert and nothing will happen. Another great reason is that smart contracts are actually pretty dumb. They do not have the ability to use bell curves or calculate the area under a curve, for example, generally speaking. Something you can't do in Solidity. There are some other math libraries that we'll talk about, but I don't really think they're sufficient either. Your other option is to go to an oracle. You can go to Chainlink for random numbers. I don't have a good way of making random numbers on chain, obviously. These are expensive and they're vulnerable. It's the #1 place to get hacked by having injections of bad information. So what data primitives do we have available? Well, Viper's got decimals, but they're locked at fixed point with 10 decimals of precision. So when you start doing these curves, you wind up ultimately with like 6 places of precision, which is totally not enough for smart contracts unless you're just doing z-scores. Solidity has uint 128, int 128, and all these others, but everything's really just uint 256. It's just a 256-bit word, actually. Technically, it's not really even a number. So good luck, have fun. You are highly incentivized to make your own primitives. So I know that there's other ways of targeting the EVM, but these are the main ones that I know about. Everybody's heard of Solidity. This is JS-like. I don't know why you would do that to a language. It's considered, very high level. It's very capable. The bytecodes are pretty large. So this is really bad for doing math. You can use Yule, which is an assembler language that inlines in Solidity, or you can stand by itself. Many people are quite happy with this. It seems really powerful. I've never used it. When I started making math contracts about 4 years ago, I used Viper because of the built-in decimal system. It doesn't offer decimal exponents, so I had to move on to Huff. Huff is my favorite because it's got a one-to-one relationship between the opcodes and the bytecode. The bytecode's really, really small, and in many cases, the gas fees are determinate. So this is really good for an intermediary contract that just functions as a calculator. So let's talk about WAD math. WAD math is essentially multiplying everything by 1 quintillion. There's not really a way around this when you're talking about bit shifters, and the EVM is a binary system, so you kind of have to do it. Lots of exchanges use the ray, which is 10 to the 27th, and others internally calculate to 10 to the 45th, and then outwardly they use a WAD or a ray so that they're compatible with other things. So yeah, if you want to represent this calculation, 0.5 times 3.0 equals 1.5, this is actually what you have to do. 5 times 10 to the 17th times 3 times 10 to the 18th, all divided by 10 to the 18th. It's a roundabout way, right? Sorry, but ultimately you have to, you scale up and then you calculate and then you scale back down. So this guy, John Napier, he's a Scottish sorcerer from 1600s. He kind of invented logarithms by accident, and he really liked WOD math. He did not enjoy long division, and so he avoided doing long division by multiplying everything by 10 million. So this is exactly the same trick 400 years ago. And so, yeah, the whole purpose of what he's doing here, he imagined one dot moving at a linear speed towards some finish line, and another dot moving at a geometric rate related to how much space it has left before the finish line. So, you know, this one would continue on, and this one would eventually get there. And now the scale is bigger, and you have essentially the first logarithms. This other mathematician called Briggs took a ship up there next year and said, hey, man, this would be way better if we recalculated this in base 10, which became known as the common log. And yeah, Napier said, I'm very old and I'm not going to do that. So he went home and did it himself and released this tables of magic numbers for the next 10 years or so, from 1617 to 1624, which reduced multiplication to addition and division to subtraction. You guys remember this from high school, yeah? Cool, yeah, it's all the same stuff. And we got pretty far on that for a very long time. So at this point, you should be familiar with the scaling trick. It is never going to change. But we follow the same playbook as Briggs in pre-computing stuff. So in fixed point 127, which is my data primitive that I'm about to explain, there's one workhorse algorithm, log base 2, because the EVM is a binary system. This has to be the workhorse algorithm that the others are based off of. And if we have this working well enough, then these ones can be computed with just multiply, shift, and add. So they become cheaper and considerably more accurate than you would expect. So what is fixed point 127? It is a smart contract and a data type, and it has pre-computed tables in it and functions to go with them. There's one sign bit, and I sacrificed one bit from the integer magnitude, so domain's a bit smaller than it could be perhaps, and then 128 bits for the fractional part, and we'll go to the full 128-bit fractional depth for all these calculations. So let's talk about the pre-computation principle a little bit. If you want to do e to the x, for example, or another transcendental function, in school, lots of times they will have you calculate it like this, with a Taylor series expansion, which is an infinite series, but usually they're just like, do 25, and you're okay. Well, I don't know if you noticed, there's exponents, there's lots of divisions, there's factorials, not cheap. And on a fixed point system, the rounding errors compound, and by the time you get to maybe the 10th or the 15th figure, you just have the wrong answer. It's not just a little wrong, it's very, very wrong. So don't ever try to use Taylor series expansions on the EVM. It's not gonna work. Here's a brief look at what we have for pre-computed values. There's natural log of 2 and its inverse. These are just numbers, and this exists for the bridge between the natural log and log base 2. And of course, yeah, square root of 2 and inverse of e are there. I think pi might be in there too, but we don't really need it. It's just fun. Just for range reduction. And then, of course, a bunch of pre-computed coefficients for minimax polynomials and for range reduction techniques. This gives a similar effect to the Taylor series expansion when it goes well, and it's considerably cheaper, but it's very hard to compute these for me. So, okay, what's the leaderboard look like? Solidity is the king right now of math libraries. Have you guys ever heard of any of these? None of this looks familiar? This man, you think king is PRB? Did you make PRB? Okay, I got scared for a moment. Very cool. Well, it's very nice. I'm very happy with this one, especially because the domain is actually so large. These three all exist within the space of uint 128, so that when you multiply numbers, you don't slam against the ceiling of the 256-bit word. But we have a different multiplication algorithm, so it's actually not a problem. Yeah, anyway. Any questions about this? This all makes sense? Okay, great. So gas versus precision. This graph is a little bit strange because fixed point 127, which is over here, let's see, oh, I got a laser. This contains the cost of static calls because it is a contract and not like a pure math library. This is the result of 41,000 different fuzz tests across all of the functions that are available for all of these libraries, given in the format that they like. So Solidity is the purple one, and it's got really, really strong precision. This is EXP, so there's going to be a range probably near 0 where the calculations don't really work out that well. The way that we got this precision in terms of digits is this is compared against an oracle that is correct to 100 digits of precision, and we just count up however many digits are exactly the same. So yeah, at the expense of a bit more gas, we don't have any variation in the precision. And that's because we iterate, and the other ones don't really iterate. So yeah, PRB math, I agree, it's really fantastic. It's very, very cool. But I also only learned about it after I started this project. So yeah, do with that what you will. Try to do some more research next time, I guess. Why is the Solidity standard? It's optimized gas for WAD math. Most of the math is safe within the WAD scale. They're really, really good at that. And they have Lambert W, the crown jewel. So this is the special function I mentioned earlier that cannot be represented with primitives. And it's useful to exchanges for calculating the depth of liquidity pools or derivative prices based on assets of other regular real assets. And people got really excited about that. But our design philosophy with fixed point 127 is ideally everything should be defined by primitive functions. But in practice, we're going to have one workhorse algorithm for your hardware, which is log base 2. And we must exhibit terminal precision, like we said. So some of you may remember IBM System 360. A long time ago, it established the 8-bit byte. Prior to that, it was common to have sets of vacuum tubes in 3-bit bytes, which is really weird. So yeah, they kind of established the dominance of hexadecimal and the ease of changing between, log base 2 and hex. So the same thing is, across 400 years, we're doing the same thing over and over. So what are the elements of a good math contract? I think they should be defined piecewise and procedurally. You cannot have loops. Things can't loop. You should start with a bit hack or a lookup table. Anybody know about Carmack's fast reverse? This Quake 3 algorithm that's very famous. It's a really, really fun algorithm. You should check it out. It's just one single procedure, and it produces like the inverse square very quickly. So this was a revolution in ray tracing, I guess. So anyway, after you get through the bit hack or the lookup table, you should use a polynomial with pre-computed coefficients. And then you might want to do fast convergence iterations. And then you may want to avoid catastrophic cancellation, which is when two numbers are very, very close together and you divide them, you get errors only. Or if things are very, very close to 0, fixed point doesn't handle them well. So you need a special algorithm to finish off. And if you want to extend the range beyond that, you might use an asymptotic convergent iteration, which I did not choose to use. So how does our 256 by 256-bit multiply works? We cut the number into two pieces, and a high and a low part. These are using extra small numbers, 12,345 and 67,890, so that it's easy to see what's going on. We're going to use a scale of 1,000. You cut them into pieces, you multiply them together, you reintroduce the scale, and then you sum them up, and that's the answer. You can check it. And this is what it looks like in Huff. At least this is the first part. So any of you who have not read or used Huff before, it's just an assembler language. It's really fun. It's very efficient, and Claude is not very good at it yet. So okay, let's talk about log base 2 of x, the most important algorithm for us. Say you want to find log base 2 of tau. Tau is the new pi. It's just 2 pi. And so we find the most significant bit, which in this case is 6, right? 6 is the first bit, the biggest chunk. And because it lies between 2 squared and 2 cubed, the integer part in our binary system is 2. From there, we can begin a range reduction. So going down with fractional powers of 2, depending on whether the boundary is before or after the value that you've got, you can add it on here. And we do this 7 times. I'm sorry, I had really cool animations, but they're not showing today. Yeah, so anyway, you get through the range reduction, and then there's the polynomial technique, and this is a 13-degree polynomial, so the first through 5th degrees get you closer, but by the time you get to 13, we've actually closed out all 128 bits. So this works pretty good, and we've reduced log 2 to essentially just bit shifting. And yeah, there's not much more to say about that. So once you get to natural log of x, congratulations, it's just a wrapper. Because we've got natural log of 2 pre-computed in the system, you compute log base 2 of x, multiply it by this, and you've now just changed bases. It is just this. Very, very, very nice. So yeah, we start with the, all right, square root. Yeah, let's talk about the Karmat bit hack approach. So for this one, we start by finding the most significant bit. Say we want to find the square root of e squared. That's what I put in here. The first significant bit is 2, and we have to shift it so that it falls in the right place within our 256-bit word. So the most significant bit in this case is actually 130. And if it's odd, then we have to adjust for that by this pre-computed value, square root of 2. But when you get through this, this first bit of the procedure, you should have about 1 bit. You should be around like 2.7 or 2.8, something like that. And then we use Newton iterations. So this is what a Newton iteration looks like. Your next term is just this. And each time that you iterate, you double the digits of precision. So this is quadratic convergence. Got you. I'm really close to the end. Thank you. Yeah, quadratic convergence. There's also a cubic convergent algorithm made by Halley, the comet guy. And there's a 4th order quartic convergence, which actually is too expensive to use for this. In this case, you only want quadratic because these are such cheap iterations. So anyway, by the time you get through 7 of these, that's the end. You've got your answer. And it looks like this in Huff. I'll give you a little second to stare at it. So the interesting part is, see, there's no loop. It's all completely procedural. So x to the y. Let's talk about how to do powers. Once you've got 2 to the x, and you've got log 2 of x, well, that's kind of it, actually. You don't really need to do anything else. Why are other libraries just integer only? I'm still don't understand this. Like Viper gives you can do a decimal base, but only an integer power, and I think ABDK math only gives you integer bases and powers. What about PRB math? Do you know? Really? Yeah, they do the same thing. Yeah, of course, the same thing. Okay, well, interesting. Anyway, on to Lambert W. This is the final algorithm that I want to talk to you about. This is a hard one because, yeah, like I said, it can't be expressed as elementaries. For this one, we start with a lookup table. So this is a curve that roughly matches this function, and we've got a known domain. So it actually does go a little bit negative. There's more here. 2 minutes, got you. But then following that, we use a fast convergent iteration. This is the Fisher-Schaefer-Crowley iteration. It was written in 1973. Based on the householder method from 1970. This is a quartic convergence. So it just converges extremely fast. But by the time you get to the end, you have catastrophic cancellation issues. So you need to use another convergence called the Iacono-Boyd. And by the time you get through that, you've reached 128-bit depth again. So click through, and by the time you get to the end, the tangent line is pretty much straight up and down. There's obviously going to be some variation in any fixed point system, but it works. Anyway, that's the end of my talk. Thank you very much. You can check all this out on blockulator.com. It is on a test net. Don't worry, you won't lose your tokens. There's some games to play. Please make a badge and stuff. And my company is called Secure Data Research. So if you're interested in any of this or how I may help you improve your mathematics, please get in touch with me after the show. Thank you very much. All right. Questions? Sir.
Lower my voice to the right level. All right. Yeah, the hard question. Floating point. All of this is great. And now we go to plus inf, minus inf, and non-standards.
I'm working on floating point right now, actually. The subnormals are the hard part.
Subnormals and sort of undefined values, what is your view on how to handle them? Because that's ultimately what there's a lot of bugs associated to different choices there, and there's also a lot of inefficiencies.
Well, the IEEE 754, which defined floating point standard in 1985, is just something that is widely accepted, right? So there's certain rounding rules that everyone adheres to, and as such, the system is determinate. It works the same for everybody, and that's as good as you're going to get, basically. There's no substitute for pencil and paper.
So you are going to adhere to those specifications. That's your plan.
I'm working on it. It's still buggy.
All right. Yeah. Fair enough. Exactly.
But thank you. Great question.
Yeah. Thank you.
Hi there. In your library comparison, I didn't see SnackMate. The math library there, it's a Viper module.
Oh, really?
Yeah, and there is lots of bit shifting and pre-compute
Sure.
and log2 magic. You should have a look at this.
Okay, let me talk to you after
Sure.
after. Yeah, I understand. There's a ton of people trying to do the same thing, but I wanted to do it on my own. Yeah. Anybody else? Okay, thank you very much, guys. You did great.